afternoon, everyone, and thank you for the very nice introduction. At first, on the first slides, I would like to give you a short overview on where these materials are used and also why we need some mechanical characterization of those. I'm basically working on functional systems consisting of polymer printed circuit boards, ceramic circuit boards, and functional components on top. And one type of functional components could be the surface acoustic wave filter in smartphones. What they basically do is to filter out one frequency within a certain bandwidth and suppress all other frequencies. In modern smartphones, in the next generation, there will be up to 100 of these surface acoustic wave filters in one single phone. And if we have a look on the cross-section of those filters, we can see that they mainly consist of a functional wave. And due to the high-frequency data transfer, what should work, there are only few materials left, and two of them are lithium tantalate and lithium niobate single crystals. Here are some further properties. So the most important properties of these materials are the piezoelectricity, but there are also further interesting properties making them interesting for applications as modulators, sensors, or detectors. The properties are based on the crystal structure. We have a rhomboidal crystal structure, can also be shown in a trigonal system, which is very similar to a hexagonal crystal system. So we have an angle of 120 degrees between two axes and a certain C to A ratio. What I now wanted to investigate were some mechanical properties, because these devices are exposed to thermocycling and drop tests and so on, and therefore we need some good strength values, also toughness values, and elastic constants are available. So I used some methods, biaxial bending and nanoindentation. One thing about the substrate material, there is the need for a low temperature dependence of the properties. So what we actually want is a low temperature dependence of CTE and a low temperature dependence of the velocity of the surface acoustic wave. These two things are very much related to the Young's modulus of the material. If we have a look on the properties of the Young's modulus in a Cartesian coordinate system at different temperatures, we can see that some directions change more than others. So what suppliers basically do to guarantee the low temperature sensitivity of the device is to find certain cuts where the functionality is provided, and also within a certain temperature range there are no big changes. So there are two different rotation angles for lithium tantalate and niobate. This is how the wafers look like. And another thing is that to enhance the functionality, one side is very smooth and the other side is a little bit roughened. We measured this roughness and found out that the smooth side is very smooth. So we have between the top, so the maxima and minima, only a difference of at the most 4 nanometers, leading to very low average roughness values of around 0.4. And these values are approximately 100 times higher for the rough side of both materials. If we have a closer look underneath the surface, we wanted to check if there is any further pre-damage due to the roughening process, and actually there is no pre-damage, no further pre-damage, as we can see for lithium niobate as well as for lithium tantalate. What I now wanted to investigate was how does the surface quality change the strength distribution of our materials, and if there could be an effect of the orientation, of the different orientation between the two materials. So I was looking for an adequate testing method and found this ball and free ball test, where a sample is supported by 3 balls on the one side and loaded through a Ford sample on the other side, leading to a very well-defined stress field on the surface of the sample, and the strength can be evaluated by the maximal load and the thickness of the sample, with another factor depending on geometry and Poisson's ratio of the material. We can see that the dimensions are very small, so we have 2 times 2 millimeter specimens, and the thickness is only around 130 microns. Some advantages of this test are that you can do very local strength measurements, you have a high accuracy due to the well-defined geometry and the low friction, and the tests can be performed in different environments. For our materials, due to the big scatter in strength values, we choose to evaluate them using Weibull statistics. So the values I'm talking about are the characteristic strength, which is basically the stress with a probability of failure of 63%, and the Weibull modulus, which is basically the slope of this fitted curve. So if we have a look on the results, we can see that lithium tantalate has a characteristic strength of approximately 1,800 megapascal, and due to the roughening process, this strength is almost cut into half. So we only have a little bit more than 900 megapascal left. The slope is, the Weibull modulus is somewhere around 5. If we now compare the values to lithium niobate, we can see that we have much lower values. And what's also interesting, that some of the lithium niobate samples reach values comparable to the highest ones of lithium tantalate, but most of them are lower. And so what we can explain is exactly this, more or less this shift on the left-hand side due to the introduction of scratches due to the roughening process. But what we actually don't know is the big difference between the two materials. But what we know, especially in brittle single crystals, is that our fracture toughness is very strong dependent on the direction of our crystals. So we know that there are cleavage planes inside of our samples, and what we want to find out was how these cleavage planes are now aligned in the rotated samples. So we have a look now in a not rotated sample. We can see very nice this 120-degree symmetry of the cleavage planes. And all three planes, if we now imagine our sample, this is the surface of the sample, we have an angle of 57 degrees with respect to the surface. If the crystal is now rotated around 48 degrees, as it is done for lithium tantalate, we can see that actually two cleavage planes are almost perpendicular to the surface and can be critical in our testing configuration. And the third cleavage plane is almost parallel to the surface and might not be activated in our testing configuration. If we now rotate in the other direction around 38 degrees, we can see that for lithium niobate, all three cleavage planes might be activated, and there is one cleavage plane with an angle of 85 degrees with respect to the surface. If we now have a look on our fracture patterns of this biaxial testing method, we can see that at every sample we can identify the two most critical cleavage planes. And also for lithium niobate, we are able to identify the cleavage planes we calculated in our model. If we have a look into the crystal structure, we can see that these cleavage planes in the rotated samples are somewhere between layers of many lithium and tantalate atoms. Unfortunately, the oxygen atoms are not in this picture. This is for lithium niobate. We can see nicely that the most critical cleavage plane is again between niob and lithium atoms. We also did some nanoindents, and we can see that we find Young's modulus and hardness for lithium tantalate and niobate. These values are quite similar to what we found in literature. But what's actually very interesting is to see that also during nanoindentation we activate the most critical cleavage planes. And interestingly, on the opposite side of the tip of our of the edge of our Berkovich intender. It's the same for lithium niobate. We can also identify the most critical cleavage planes. And here we can also see nicely some lateral cracks due to the transparency of the material. So to summarize the results, we saw that the biaxial characteristic strength of lithium tantalate is more than 2 times higher than for lithium niobate for same surface qualities, that the roughening process reduces the strength by a factor up to 2, and that the orientation can have a big influence on the strength, because we were able to identify the cleavage planes for our biaxial bending method as well as for the nanoindents. I would also like to give an outlook, because we actually do not really know at the moment why this characteristic strength of dentalate is so much higher than for niobate. So we will investigate if there are any residual stresses. I'd also like to find out if there are any contributions from the piezo effect on the mechanical properties. And we'll also try to identify the toughness of the most critical cleavage planes, making some fibbed and notched lateral samples, and the samples will be tested in situ in a SEM. Thank you.